All right, let's just get right into it. Welcome back to The Explainer. Today we're taking a really deep dive into an absolute game changer in AI orchestration. We are unpacking Sentient AGI's brand new paper on the ROMA Framework. That's Recursive Open Meta Agent. Look, if you've ever tried to build an AI agent that actually finishes what it starts, you are absolutely going to want to pay close attention to this.
So let's kick things off with a question that I'm sure hits close to home for a lot of you. Why exactly do autonomous agents fail so miserably at long-horizon tasks? We have literally all been there. You give your AI a complex, multi-step goal, and then somewhere along the way, it just completely loses the plot.
It's like this bizarre Jekyll and Hyde situation. On one hand, current AI is incredible at short tasks. Give it a single-step prompt, boom, high success rate. But then you look at long tasks, and it's just a cascade of compounding errors. Think about it. A single hallucination? One bad tool call, maybe a weird observation early on, it doesn't just fail that one step, it snowballs. It propagates downstream and completely derails the entire workflow.
So here's our roadmap for today. First, we'll look at the long horizon AI problem. Second, ROMA's recursive architecture. Third, the 4 modular roles. Fourth, GEPA plus prompt optimization. And finally, state-of-the-art benchmarks.
All right, part 1, the long horizon AI problem, context rot and brittleness.
When you actually pop the hood and look at why modern agentic systems break down, you see they basically just stack tasks sequentially in a flat context window. You get this massive linear pileup of logs, intermediate traces, tool outputs. It just grows and grows. And that leads to exponential token growth. So what happens? Context degradation. The model literally forgets what it's supposed to be doing, loses sight of the core instructions, and eventually, it hits that hard context limit exhaustion. The whole system just chokes.
Moving on to part 2, ROMA's recursive architecture, a domain-agnostic solution.
So how does Sentient AGI fix this? Well, enter ROMA. By definition, the recursive open meta agent is a domain-agnostic framework, meaning instead of slapping on all these task-specific duct tape hacks, it actually standardizes the agent architecture itself. It coordinates multi-agent systems using recursive, dependency-aware task trees and structured aggregation. To put it simply, it's not a new model. It is a completely brilliant new way to orchestrate the models we're already using.
And here is where the math gets really cool. In a standard system, flat scaling means your context grows linearly, big O of n, right? But ROMA flips the script to logarithmic scaling. By compressing data at every single level of the task tree, your active context size scales logarithmically. Mathematically speaking, this basically bulletproofs the system against token exhaustion. You can run incredibly deep workflows, and you just never hit that context wall.
All right, let's get into the mechanics. Part 3, the 4 modular roles, the core control loop. So how exactly does ROMA pull off this logarithmic compression in practice? Well, think of its core control loop like a super efficient corporate team operating on a strict plan, execute, aggregate cycle. Whenever a new objective hits the system, it flows through 4 specific modular roles: the Atomizer, the planner, the executor, and the aggregator. Let's break these down one by one.
First up, we have the Atomizer. Think of this as the initial diagnostic gate, kind of like a triage nurse. It takes a look at the incoming goal and spits out a simple Boolean classification. It's asking, is this task atomic? Meaning, can we knock this out in one step? Or does it need structural decomposition? And then it routes the instruction exactly where it needs to go. Now, if the Atomizer decides a task is too complex, it kicks it over to the planner. This is your project manager. The planner's job is to isolate complexity by carving that massive goal up into manageable subtasks. And, crucially, it maps out the sequential dependencies as a directed acyclic graph, or a DAG. Basically, it's telling the system, hey, do tasks A and B at the same time, but do not even think about touching task C until they're done.
Once we've got those bite-sized atomic tasks, they go to the executor. This is the individual contributor doing the actual heavy lifting. The executor resolves tasks using 4 hard-coded protocols: search, think, write, or code. And here's a detail I absolutely love. Code execution happens inside secure E2B container sandboxes. That means the agent can run dynamic code all day long without ever risking the host system. It's totally safe.
And wrapping it all up, we have the aggregator. After the executors finish their jobs, the aggregator steps in to collect the work. It operates as a semantic filter. It takes all those raw, messy child outputs and logs and compresses them into one clean, synthesized summary. This bottom-up synthesis, this is the magic bullet that stops context rot.
The parent node only ever sees the polished summary, not the crazy scratch pad of work that went into it, keeping your context window totally pristine.
Moving on to part 4, GPA plus prompt optimization, evolving the architecture. So you might be wondering, how do you adapt these 4 roles for highly specialized domains without burning thousands of dollars on fine-tuning? Well, Sentient AG introduces GEPA plus, or the Genetic Pareto Prompt Proposer. This is a slick evolutionary optimization algorithm, but the real genius here is that it refines prompts across the entire modular hierarchy at the exact same time. It guarantees that if you tweak a prompt for the planner, you aren't going to accidentally break the strict input-output contracts that the Executor or Aggregator rely on.
The actual GP+ loop is super fascinating. It kicks off by generating prompt proposals, runs them through strict pydentic contract verification to make absolutely sure no schemas get broken, and then hands them over to local judges for evaluation. From there, it uses Pareto frontier selection, which sounds fancy, but it just means it's finding the perfect balance between conflicting metrics like accuracy versus latency. Finally, it merges the best candidates. You guys, it is literally automating the entire job of a prompt engineer across a massive task tree.
And what does all this get you? GEPA Plus drives a really impressive absolute downstream accuracy bump of up to 6%. And get this, it does it while requiring 3 to 4 fewer metric evaluations than your standard genetic prompt algorithms. It is wildly efficient, fully automated skill acquisition.
All right, final section, part 5, state-of-the-art benchmarks, empirical proof.
Just think about the massive margin on the SEAL0 benchmark. This specifically tests reasoning over conflicting web search evidence, and ROMA search absolutely dominates. It hits 45.6% accuracy. To put that in perspective, that is a huge leap over Kaimi Researcher at 36%, and it completely vaporizes specialized commercial systems like Gemini 2.5 Pro, which is sitting way down at 19.8%.
And it's definitely not just search. ROMA proves its weight in gold across the board. Take EQBench for long-form writing. ROMA, paired with an open weights model, achieves parity with Claude 3.5 Sonnet. Over on the Frames multi-hop reasoning benchmark, it hits state-of-the-art. Honestly, this proves that if you just structure your task decomposition right, open models can go toe-to-toe with the most highly optimized proprietary systems out there.
But, benchmarks are one thing. What about the real world? Well, the paper highlights the Sentient Market Reader. This is a live Kalshi algorithmic trader running on ROMA. It deploys a sentiment agent to process breaking news and a probability model agent to crunch the underlying math. Pushing all that through ROMA's solve loop lets it process qualitative and quantitative data simultaneously to execute actual live financial trades. Talk about a stress test. It's handling real money.
I really love this quote from the source material. Argamail provides the backbone. The real breakthroughs will come from what the community builds on top of it. I think that perfectly sums up the philosophy here. The framework is open source. The whole goal is to democratize access to transparent, community-owned AI orchestration, rather than sitting around waiting for the next closed-source black box to drop.
Which leaves us with one final, pretty exciting question. Now that you've seen how this recursive, decentralized, completely verifiable architecture actually works, how are you going to use it? The ROMA repository is out there right now, just waiting for builders. Thank you so much for joining me on this explainer, and I seriously encourage you to go explore the code for yourself. See you next time.